Okay, let us start our afternoon session. And the first speaker is Wei Li from the Institute of Theoretical Physics of Chinese Academy of Sciences, who will talk about AdS3, quantum gravity, and finite-N. Let's welcome the speaker.
Thank you very much for the introduction. Thank you for the organizer for giving me this opportunity to present my recent work. And I apologize for to people for coming here based on the title that I gave in this printed program. I changed my mind because I wanted to do some recent stuff. I want to hear people's opinion on this. Yeah. So I'm going to talk about so the title is AdS3 quantum gravity and finite-N. So actually, I'm going to give 2 half-an-hour talk and on 2 different stories, and they're like just vaguely related via this AdS3 and finite-N. So so the part 1 is based on this recent work with Matthias Gabbardil, who's in the audience, and we look at the chiral algebra of the 40N-4 super Yang-Mills. And so the chiral algebra is N-4 superconformal algebra with this the following generating field. So the generating field has a conformal dimension equal to the SU2R spin, and they're starting from 1, 3 half, and all the half integers. So this is very similar to the another N-4 W infinity algebra that appears in the higher spin duality. So it has very similar spectrum, but there all the SU2 spin, they're actually 0. So they're scalars. And the central charge is given by this -3 n squared minus 1. And so we start from this, but we consider the algebra abstractly, meaning that we use the same generating spectrum, but we remove the cutoff. And then we want to solve the most general structure by only acquiring associativity. So the result of this associativity analysis is that first, the C turns out you can analytically continue this C away from this point. So C can take any value. So this is similar to the this other higher spin N-4 algebra. And maybe this is not very surprising, but the somewhat surprising result is that there's no other parameter. So meaning that the algebra is rigid. So this is already different from this other higher spin algebra. So there it has 2 parameters. And an even more surprising result is that this algebra, so of course they will truncate at the these values. But the slightly surprising result is that we didn't see it doesn't truncate at C equal to 6n, which corresponds to the central charge of the symmetric orbifold. So I explain why we expect the C to truncate at these values, because some argument from the 2C holography. So it seems that this expectation might break down at the finite-N. So I will discuss some possible resolutions. So this is the first story. And so the second, so from this 2C holography, so we expect this chiral algebra to be given by the BPS part of the computation independent of the AdS3 cross S3 cross T4 spectrum. So you first have to decouple the T4 and then also take the BPS part. But that expectation is from the n goes to infinity analysis. So we have some worksheet argument also imply this, but this is a large n result. So when we go to the finite-N, we see that this decoupling of the T4 would might break down. But I mean, I think I just have to stay if you want to hear that story. I think I just have to stay for another 20 minutes to hear that. But so yeah, let me summarize the second story. So second story is on the physics is not that related. So we want to understand the string exclusion principle by the finite-N expansion, but for the AdS3 CFT2 holography, and we'll only look at the half BPS sector. So as we know, the AdS5 case, the finite-N expansion is realized by this giant graviton. So what do we see? So this is work in progress, but what we already see is that for the AdS3, So these Bob saddles from this expansion correspond to certain orbital. So you're orbifolding the AdS3 cross S3 part. And then there are also, so this is very similar to the giant graviton expansion. You see this alternating signs in the one loop partition function. So this will give you the cancellation and then produce the truncation. So this is the punchline. So let me start with the first part. So, so we have this SCFT VOA correspondence. So has basically you start from 40 into 2 superconformal CFT, and you apply this procedure, and you obtain a chiral VOA. So I explain a procedure that's slightly different from the original one, but more parallel to this later holography picture. So you basically place this 40 theory on the C cross R2, and then you turn on the omega background on this the R2 direction. So and then you do a holomorphic topological twist on this whole thing. So holomorphic is the C part, and topological is the R2. So means that you define the superchart, and you such that the translation along the 3 and 4 direction, and also the anti-holomorphic direction along the C, they're all Q exact, and then you consider the Q homology. So the end result is that you only left with the holomorphic part of the theory that's lives on C, the holomorphic part of C, and then the Q homology give you generate a VOA here. So in particular, they are given by the short subsector of the alternate theory. It's a quarter BPS and satisfy this the charges satisfy this condition. And the character of the the character of UA will reproduce this short index. So from the from the 40 data, you can obtain the 2D data this way. So the 40 superconformal central charge is multiplied by -12, give you the 2D central charge. So meaning that this is always non-unitary. And this is also the 40 flavor symmetry give you the central charge give you the level for the 2D affine algebra. And also the short index give you the characters of UA. In particular, if it's no line defect, it gives you the character, the vacuum character, and if the line defect give you the character of the higher representations. So today I'm going to focus on the easiest case, the 40 into 4 super Yang-Mu. So the spectrum is already worked out. So it has an into 4 superconformal part and all this into 4 BPS multiplet. And most important thing is that the SU2 spin is equal to the conformal direction. So this is very similar to, as I said before, this is very similar to this higher spin into 4W. And there is all the J equal to 0. And another difference is that here, all the bottom components, they are bosonic, even for the half integer. So this is also is very important for the analysis. And the central chart is discretized this way. So we want to consider this. We want to start with this spectrum, but consider the algebra more abstractly. So first we want to remove the cutoff. So we just take this spectrum and ask the 3 questions. So first is whether C can take a continuous values. And remember that the answer is yes for the other W algebra. And the second is whether we can deform this algebra, i.e. whether there's additional parameters. So this is also yes, because the other one has, apart from the central charge, the other algebra has additional parameter that's given by the OP coefficient of the 334. And then finally, when does the algebra truncate? So let me briefly summarize this associativity analysis. So this is the no, that's not important. It's just that sometimes the people somehow are more familiar with this algebra coming from this higher spin AdS3 duality. And certainly I know this algebra before I know this algebra. Also, this is somehow actually easier. For example, this one has a cosine realization. You can know this one. It doesn't seem to have. and people just know more. So this is you can view this as a benchmark. So this is the input of the associativity analysis. We give this a spectrum, and then we just solve the OPE coefficient constrained only by the associativity. So I would reduce this Tillemans mathematical package. Otherwise, I wouldn't be able to do this computation. And for example, if you want to study the associativity of this three field, so you just make ansatz of the three half, three half. So on the other side, you see that you make the most general ansatz. So you see that the spin 2 will appear, and there's also all this coefficient from the into 4 superconformal part. So L is stress energy tensor, and this spin 1 current. So the coefficient here, they are kind of boring. They can be fixed by the associativity with into 4. And then because this one give you W2, so you also have to make an ansatz of the 3 half and 2, and you also get this coefficients. And then you just solve this associativity constraint. You get, for example, this constraint. So this problem is graded by the sum of the conformal dimension here. Just solve it order by order, and you get this kind of constraint. So you already see that there are 3 things that you notice is that first AC can take any value. So B, that there's you don't see any additional parameters. So that meaning that the algebra is rigid. And finally, all these constraints, they are rational functions. So so this rigidity statement might be useful for something for some proof or give this explanation of some stuff. But today I'm going to focus on this last bit. So they're all rational functions C. So so the truncation means that when the C takes some special values, the fields above certain conformal dimension they will decouple, meaning that they close among themselves. Then you can just quotient them out. So in particular, you can see this from the poles and zeros of all these fractional functions of the constraints of the OPD coefficients. So these poles and zeros will indicate where the algebra might truncate. But then remember that when we solved it, we didn't allow for null vector. So it might not be the place where they actually truncate. So you have to check them explicitly and allow for the null vector. So the result is we see this truncation at this point, and this is reproduce the central charge of the Cairo algebra of the algebra theory. But the surprising thing is that we didn't see the truncation at this point. So let me try to first name why do we even expect that we will see the truncation at the C equal to 6? So this is the question that we could ask earlier. So let's consider the holographic version of this CFT BOA correspondence. So this is a noisy slide. So this is the holographic setup of the parent theory. So we start from this string setup, and the word volume theory is into 4 super young mu, and the holographic deal is the AdS3 cross S5 supergravity. And then we do this holomorphic topological twist. So here you get the topological string theory with this additional D2 brane wrapping on C over C3. And on the boundary, you get this Cairo algebra. And on the bulk field, you get this topological B model in the SL2C, which is basically AdS3 cross S3. So here you already see that there's an AdS3 cross S3 here. And this are related by this Tracy holography of Galto and Cosello Galto. So you can also see this from the worksheet theory. So I start from this worksheet theory of Gabriel Cooper-Coma. And I asked where does the short subset, the Cairo algebra sit inside this? So it turns out it sits inside also a AdS3 cross S3 sector, the BPS part of the AdS3 cross S3 sector of this worksheet theory. So from both the Tracy supergravity and the worksheet argument, you see that this Cairo algebra on the dual side, it should agree with the compactification independent part of the BPS spectrum of the AdS3 cross S3 cross D4. And remember that the AdS the super Yang-Mills, there correspond to the R flux. So its subsector, its chiral algebra sector should also have the R flux. And on the other hand, we know that this background with NS flux should be due to the symmetric orbit for the T4. So you have this chain of argument. If you believe this, then the algebra should truncate at 6n. But we don't see this truncation. So something must break down. So the truncation, the C to 6n. I mean, that's the central charge of this symmetric orbital. The central charge of the symmetric orbital here, that's the C to 6n. Truncation means that you imagine that the C is arbitrary, but at C takes some particular value. All the fields above certain conformal dimension, they close among themselves. Then you can quotient. I mean, it's just like a Wn. W infinity would truncate at the Wn. At say the free formula for the C. So something must break down. So I offer some. That's what I'm going to say now. I mean, if you believe this chain of argument, then you should see the C equal to 6n. So because we didn't see this truncation, so something must break down. So it may be telling us something that, I mean, this is all common folklore. So maybe something, not common folklore, but something might break down. That's what I want to say now. I have to explain the box a bit. Right, so the box is, I start from the AdS5 cross S5, that says R flux. So I'm looking at the current algebra subsector. So that's, and want to relate it to the background of AdS3 cross S3 cross T4. So because the parent series has R flux, so I expect the child series also has R flux. But and then I'm looking at the BPS spectrum. So supposedly, it shouldn't. It's a BPS, so it shouldn't change when you move around the moduli space. So that's when you go to our NS flux. So at NS flux, there's still to the symmetric orbital. So, but many of this is about the infinite N, and also you're not truncating the T4. So the possibility might be N first is T4 K3. I mean, so this spectrum, you don't see the T4 excitation. So that's why I say it's computation independent part of the BPS spectrum. I mean, when you look at this spectrum, when you try to see how they sit inside this AdS5 cross S5, they look like this AdS3 cross S3. And they, in particular, also look like a subsector of the AdS3 cross S3 cross T4 series, but without the T4 excitation. So that's why I call this communication. So you're coupling the T4 to see this. Yeah, this is the night expectation, but it's wrong. I mean, something's wrong. I'm saying that you assume this is true, and then you seem to want to conclude that C should truncate at 6n, except that you don't see the truncation pattern. So something must be wrong. So I'm offering some possible resolution here. I mean, depends on. I mean, it depends different days. I like one more than the other, but I'm not sure which one. But no, it's not a deformation. I mean, from this. I'm actually doing some twists to get into this subsector. It's not just. I just think that it's natural that this subsector should also have the R flux. I mean, because the child theory is a twisted version of the parent theory. I mean, the twisting you're localizing to a subsector. Because no, because say it again. But I'm only looking at the BPS spectrum and the communication independent part. So if I compare the look at the spectrum, it is true that it's just given by the spectrum of the AdS3 cos S3 part of the spectrum of the worksheet series, but with a different physical state condition. I mean, the spectrum all works fine. It's just that the algebra seems to be off. So it could be that so I have to come up with this four possible resolutions. That it could be that even for the BPS state, even for the BPS states, when you move from the R flux to NS flux, you might encounter some wall that some singularity that prevents you from moving, or maybe this decoupling of T4 based on the finite-N. Because it's an argument that the AdS3 supergravity and the worksheet argument, they both assume the large N. It could be, yeah. I mean that's I don't know which one of this one. I mean, and the other one is and also this N. The nature of N is kind of different for the 4D and the 2D case. So here is the number of D3 and here is the number of F1. So you might think that maybe this N it's not conserved here, but I'm not sure. And the final one is a more prosaic solution. Maybe it's just you have to tweak a bit at the small low speed part. Yeah. So that's why I want to talk about this here, because I want to hear what's other possible resolutions here. So yeah, let me summarize. So we'll look at this chiral algebra, this N4 chiral algebra from the 4D into 4 super Yang-Mills, but abstractly. And then we remove the cutoff, and then we solve with by associativity. And we see Y-C can take any value 2. The algebra is rigid, and the algebra doesn't truncate the 6N. It's that seem that some expectation, the expectation from the twisting probability seem to break down here. I think I need to go to the second. So one quick question. The cutoff is the spectrum. I mean, here, when you really look at the chiral algebra of this thing, the spectrum stop at the input 2. I mean, the spectrum itself has a cutoff. Here, I mean, I want to solve for the most general one, so I don't impose a cutoff. Yes. Yes. No, if I don't truncate, see, when I solve this associativities, there's no constraint on C. I have all this, it's a rational function C's. So, okay, then I move on to the second. You can ask me later. I move on to the second, because this is also a pretty long story. So, so basically, we want to study how the string exclusion principle is realized in the AdS3 quantum gravity. So let me quickly remind you the role that the big N plays in the AdS3 CFT correspondence. So the weakest form of the AdS3 correspondence is that the N goes to infinity. It's the planar limit correspond to the tree level string. So the planar KFT is equals a classical supergravity. And then this intermediate strength of the correspondence, that's a large N, but including all the symptotic 1 over expansion. So meaning that the non-planar CFT is QFT is given by the semi-classical supergravity. So the non-planar correction corresponds to heterogeneous correction in the string and the loop correction in the supergravity. And the strongest form would be that this is really true for the finite. And so this is if you uses Van Neumann algebra language. So I just want to say they're truly different algebras. So yeah, this is just a picture to see where we are. So normally this is the parameter space. So the vertical direction is the genus fraction, and then this is the truth coupling. So normally we start from the boundary of this graph, and this was kind of hard to go to the real interior. So today I want to talk about this finite-N from the gravity point of view. So from the DOCFT, there's no mystery. You could just set the input N is finite. So the question is, how do we produce this straight finite-N QRT result from the gravity side? So it's not as a 1/n expansion. It has to be truly finite-N. So in particular, I want to see how to see this extreme exclusion principle explicitly. So let me first quickly remind you what is string exclusion principle. So you look at the boundary DOCFT and finite-N. So we know that finite-N CRT has to have a fewer states than a larger N. And the number of states should decrease as N decreases for fixed energy. And for example, so how this is realized? So for example, if the AdS3 case is realized by the so-called trace relation. So if this matrix is infinite size, then all the single trace operators are all orthogonal. But I find that I get trace relations. So this will cut down the number of states. So for the AdS3 CFT2, so if you use this symmetric orbifold description, that just means that the total cycle length cannot be bigger than N. So you know what's going on at the CFT side. So for the bulk gravity, so because it's a finite-N, you want to include all the non-perturbative effect. But naively, when you want to include the non-perturbative states, naively you should have more states than the perturbative gravity, and then this number of states should increase as the G string increase. So the string exclusion principle so says that so somehow this non-perturbative effect have to somehow cut down the number of states instead of increase the number of states. So there must be some goals like structure. So this is rough hand waving argument. So the point is to see how to realize this. So this is the goal. The strategy is to do this finite expansion. So strategy is you start from the grand canonical ensemble partition function. So if you can get this, there are two ways to obtain the finite the canonical ensemble partition function. So you can just obtain this as an expansion of the zeta n term. So this will be the finite answer from the CFT side. So alternatively, you can also get this by a contour integral. And then, so this is from the definition, and then you deform this contour. So the choice of contour would depends on the regime of this all these other fugacities. And then you decide you first find what's here. All the bulk, you have to first determine all the bulk saddles that reproduce finite, and then found that this bulk interpretation for all this. So the exclusion principle is just realized by the fact that here you should see some alternate signs that they'll give you the cancellation. So, no, it doesn't have to. You do this, and then the point is that if you can interpret all this as a bulk saddle, then you get a bulk interpretation of the finite. Right, but you have a pole. Maybe you can see that later from AdS3. It's a family of poles that combine to give you a bulk saddle. So the goal today is that I want to explain this the mechanism of the string exclusion principle for the AdS3 case. So let me first review the AdS5 case that's people more familiar with. So I look at the HPPS partition function. This is the simplest case for this story. So this is the grand canonical partition function, and you see that there's only simple poles at this Q minus K here. So first, you compute the Zn by expansion. So this is the result. And then this is the result of the contour integral, like this. So now we want to find the bulk interpretation of each term here. So this is the result here. So the Z infinity is just a background closed string spectrum becomes the BPS KK modes. And then this guy is supposed to be the open string excitations on K giant graviton grades. So the giant graviton on the QFT is given by this determinant operators. And in the string theory, it's just a K giant graviton D3 wrapping on the S3 inside S5. So if you look at this, you see that there's 1 over you see this oscillating factor. So this will give you the cancellation. And you also see that you compare this one with the this expression. So in this case, this is equal to the D3 brane partition function with the Q inverse. So from that point of view, it's a negative mode. But then you want to analytically continue from outside the unit this inside. So this analytic continuation is basically a rewriting of the previous expression into this form. In this rewriting, you get the this negative signs, and also the negative modes become positive. So I want to imitate this and try to do the AdS3 case. So the setup is just a D1, D5, and the supergravity is this AdS3 cross S3 cross T4 or K3 with the N flux. So it's on the same moduli space as a symmetric orbital, and when there's one NSN flux is due to the symmetric orbital. So I want to just look at the high BPS sector. So it's just either NI sector is just given by the parallel. So this is the one canonical ensemble partition function for parallel primary in the NI sector using this DMEV formula. So this H is the Hodge number of the T4 or K3. So I start from this result. First, I just do the expansion to get the field theory result of the finite-N and to see what we should expect. So in this talk, I'll just focus on the K3, and then I will set the T equal to, Y equal to Y bar. So this is the N equal to infinity result, and this is the N equal to 1, 2, 3, 4. So what are you seeing? So remember that for the 2D CIT, there's this classification of the light, medium, heavy state. So because I said Y equal to Y bar, so I can consider the total conformal dimension. So when the total conformal dimension is this range is light, and when it's above this range is heavy. So what's in the middle is the medium. So for the case at hand, so this is the how you should expect. So less than N, half of N is light, above N is the heavy. What's between is the medium. So this is precisely so what you see. So blue are light states and the red heavy. So for example, you're supposed to match the KK spectrum up to the only with the light state. So indeed this is true. So only have the space to show here. So you're matching this match this part. And above the Y to the N half N, then the gravitational back reaction will start to set in. So that's from the medium and heavy. So the heavy states appears at the N. Also, you see here. I mean, you can find some integer meaning for the integer coefficient, but I won't be talking about those today. So also at finite N, this heavy state also truncate. So the goal is to somehow using this finite expansion to explain the medium state and the heavy state, in particular the heavy state. Yeah, so that's why I said that's why I have this. I mean, the black hole is, I mean, has a biggest, it's a peak, the degeneracy peak at this point. Yeah, I want to say that I want to just emphasize that from here is all heavy state. I mean, for this giant gravitational expansion or the finite expansion, you only see the medium state, but somehow the medium state will also give you all the degeneracy of the heavy state. So that's the mechanism that I want to explain later. So yeah, I want to reproduce all this integer coefficient from the finite finite expansion from the gravity. Yeah. Maybe I think it's not important whether it's black hole or not. Here, I just want to say it's a heavy state. Normally, when people say heavy, this about the black hole. I think the point is that so all these orbitals, they are medium state, just like the giant graviton. I mean, the question is why this can be heavy state. So we just do the contour integral. So we start from this grand canonical partition function, and here I list the Hodge diamonds here, it's T4 and the K3. And then you look at the poles. So there are four family of poles that basically come from this four corner of the Hodge diamond. They are the same for both cases. And then there's also a wall of essential singularity that from the center of the Hodge diamond. And then this four family of poles give four types of saddles. So this question that Jimmy asked is not that each pole corresponds to a saddle. Here you have to this sum over the n. So they're labeled by k and n. They're labeled by k and n. So for each k, you're summing. If you sum over all the n, that corresponds to a saddle. But this you have to see later. You can only see later. So because of this, we have this wall of essential singularity, so the residue theorem doesn't apply anymore. So you actually have to analyze which saddle contribute, and this depends on the regime of this y and y bar. So for example, when the y and y bar they're the same and both smaller than 1, only the minus contribute. And so this is some detailed analysis. So I will just show you the case where the simplest case here. Yes. I mean, in this case, it's a sum over for fixed k. Each k corresponds to a saddle, and for a fixed k, sum over this n. It's like it looks like a circular overfold. I mean, you'll see more later. So first, let me show you that this is indeed this selection of the saddle indeed works here. So I mean, it can't work. It can't be better than finally. It can't be better than 1. I'm looking at this into 1 case. So this is final end result. I want to compare this from a sum over this saddles from the from this residue contribution. I mean, right now I'm not sick whether it's a bulk or not. So the k is cut off. So if I just sum over just one of them, this result, you only match 1, and you sum 2, you already give the 2's match, and then you see already. So first thing you see that there's a huge oscillating of the signs, and so there the small k equal 2 must be negative 2 to give you the negative signs in this total result. And then you see this you reproduce the correct result with the correction. It's like a very fat tail. It gets fatter and fatter when you put more term, but it's also staying more and more away. It's like your trouble is bigger and bigger, but you also further away. Yeah, no, it's not. I mean, in fact, it's going bigger. Right? It's the tail is fatter and fatter, but it's also further and further away. It's definitely not right. I don't have the detail, but this is the leading one, right? I mean, the later one. Look, and this is 24. I mean, this is huge number already. Yeah, I mean, there might be some meaning for this leading one, but yes, yes. I mean, this is all thing that here they're zero. Every second. But yeah, I mean, there are more questions that I can answer, but that's a good question. But that's not the point I want to emphasize now. So this is a K equal 2. I mean, it's similar, but I find this matching at the N equal 1 already quite striking. That something nice is going on. So now it seems that the prescription on selecting which poles that seem to work. So now I want to find the bulk interpretation of this term. That's the question. So first, you know, the n to infinity, the pure supergravity part should be given by the pole that closest to the origin. So here that's given by k equal to 1 minus minus here. And the observation is that all these other four corners, you can obtain it by starting from this minus minus and do some bulk spectral flow. So that means that we only need to understand this. So let's just first understand it minus minus. And so the statement is that this comes from the character partition function of this orbifold. So this is the orbifold that I'm considering. So this is the metric. The orbifold action is I'm orbifolding a circle in the AdS3 and another circle in the S3. So this is exactly orbifold. So so we expect this to be independent of the position modular space. So we can, in particular, consider NS flux. So when you have NS flux, there's a worksheet description. When there's only one unit of NS flux, we can use this worksheet description. So that will allow us to see that this ZK comes from the character partition function of this in this background, and then this result should apply across modular space. So this is the worksheet that's given by Matthias Gabriel, Bing Guo, and Samir Matou. So so this is the worksheet of the tangential string in this. So if there's no ZK orbifold, the spectrum is given by a sum over all spectral flow sector where the spectral flow is integer. So they observed that if you want to consider the orbifold K geometry, so now the spectral flow should be fractionally quantized by this K. So in particular, so now it's the W still can be integer, so that corresponds to an twisted sector, and for the fractional, they will be correspond to the twisted sector. So for the dual CFT before the ZK orbifold, this is symmetric orbifold, and the result there is that for the ZK orbifold, they correspond to a subsector of the original orbifold, and but with a new vacuum given by this K strings. So this is a non-perturbative vacuum that's very high above. So we just take that, and then so there's some this so the final ZK invariant state. So if you consider the worksheet, you have to perform that at the level of single particle. I mean that corresponds to the single particle spectrum, because we're looking at the full DOCFT or the full bulk result. It corresponds to the multi-particle spectrum. So we take the single particle spectrum, we do the multi-particling, and also there's some tree level contribution, and then in the end we do a projection. So the projection have to be done after the multi-part cleave. And then there's some prescription, and then in the end, only so in the middle, you have all this fraction mode, but the final result is there's only positive. There's only integer mode, and so in particular, so remember I said earlier that for the AdS5 process, AdS5 CFT for case, so there is this negative mode, and then you do the analytic continuation, you get they become negative and they become positive and produce this alternating signs that give you the cancellation. So here is a similar. So this is just example. This is all the for n less than k, they're all negative. So you do analytic continuation, you get they become positive, and then you have this sign. So this will push the medium state to heavy state, and the oscillation would give you the cancellation. I'm trying to see this mechanism, how this appears in the AdS3 case. So for the AdS5 case, so this is the giant graviton result. You can write it. I mean, this given by this, but they're negative mode. So you have to analytically continue to inside the unit disk. Then I mean, this is equal. I mean, you rewrite this, you see you have this sign. Yeah. Yes. I mean, this is this is a work in progress. We haven't done all that, but here we already see the sign that here this is a negative mode. We have negative modes here, and here the negative modes. If you do the similar thing, they also, I mean, this oscillating signs produce this cancellation. Yeah, I mean, we don't have a. No, I think it's it's a same type of negative modes. I mean, if you look at this, it's also negative. Well, we don't. I mean, we don't have a competition directly to give you this. We have the worksheet competition that give you this, and then you do. No, I'm not doing anything. I mean, from here to here is really a rewriting. But I mean, in this rewriting, this is why bar there less than 1.
No, but it's not so simple. This appears
What is pure? What is pure?
Why?
Yes.
Not opening.
But on both sides, the y, on both sides, the y is yeah. I mean, it's a finite product, but it's an infinite series. So this is a summary. So we did this finite expansion for the character sector, and it was the analog of the giant graviton case is this orbifold, and the mechanism to realize this string function principle is very similar to the AdS5 case. And let me remind you the summary for the part 1. We studied this Carrel algebra, and we solved this just by associativity, and we see that the A C can take any value, and 2, and this algebra is rigid, and 3, that we don't see this truncation that you might expect to see from the Tracy holography. And summary for the whole talk is that when you look at the finite-N, you seem to see some intricacy that you don't see before, and we want to generalize to other sectors or other dimensions and compare to other finite-N approaches. That's it.
Do you have any questions?
Yeah, I mean the finite-N, I guess. The finite-N. I mean, I would hope that the resolution for the first part is truly a finite-N, but see AdS3. What happened there? So that you just see the chiral algebra that you start. It's negative. Yeah, it's negative, but that's it should be negative because it's a non-unitary from this relation. Right. So from all these rational functions, I mean the poles and the, for example, this one is C equal to -9. So that means that this one blows up. So if this has a solution, means that the n3 half has to be 0. So that means that it truncates at the into or superconductor. But everything above 3 half drops out. But you want to talk? Is this here?
Well, what happens at, let's say, 3, 6, 8?
Right, that's the point. So you see this poles and 0. So they suggest that it might truncate, but to really check it truncates, you have to really you see they might truncate. So you put in the spectrum, and then you have to solve it to see whether the C is there. For example, you see this C equal to 18. So that's a 6n, right? But we'll solve it 6 that is not there. So some of them are spurious. So this is the only indication that the word might truncate, but you really have to check again and allow for the null vector to really solve it again.
So I'll ask again because it didn't. So what was the expectation of implicit holography that breaks down and finite-N? What breaks down?
So the Tracy holography doesn't break down, but the expectation when we move from the infinite-N to finite-N, that might break down. So from this expectation, you see that here you should see this chiral algebra as a compactification independent part of the BPS spectrum of this statement. But this is an infinite statement. So I mean this truncation pattern is finite. So we'll do the maybe this truncation decoupling of the T4 somehow is not clean at finite.
Favor?
The first two I think this one it will be very boring. And this is, I mean, as the second part showed that N is not that different. And there's still lots of similarities. But I will hope for either of this, maybe this one.
More questions? Not, then let's thank the speaker again.